What's up, everybody? Welcome to another lecture about chemical reactions. In this one, we are going to go in to balancing the chemical reactions and what that looks like. So I'm going to try to do this without using a ridiculous amount of time, but that means I might go a little bit quick. So if we go back and think about a couple of the other lectures, we were talking about Antoine Lavoisier and how he came up with conservation of mass using the decomposition of mercury to oxide, or mercury to oxide breaking down into liquid mercury and gaseous oxygen. All right, we can see the equation is written here. And we also know that he found out there were the same masses on each side of the equation. However, if you take a look, there's one mercury on the left, one mercury on the right. One oxygen on the left, two oxygens on the right. So if I added up the atomic masses of everything on each side of the arrow, I wouldn't get the same number. And because we know the masses from before and after the reaction are the same, the masses from before and after the arrows have to be the same. All right? Now, we can't go in and just add a little 2 right there with the oxygen because that means we are changing the chemical. That is not an option. And we can't go in and get rid of that little 2 right there. That's not an option either because that's not something that, exists easily in nature. Oxygen likes to exist in little molecules of 2 oxygen atoms. All right, so again, we would be changing the properties of the chemical. And we can't do that because we know what chemicals are there. So we got to do something a little different. And that's what balancing chemical equations is all about. All right, so what we have to change is we have to steal some math words. All right, and we need to fix the equation through this process called balancing. And what we do is we add these things called coefficients. And if you think about it in terms of math, a coefficient is a big number before a variable. All right, we see this a lot in algebra, like 2x equals 4. All right, that 2 that comes before the x is known as a coefficient. And when we have those coefficients, we are able to balance the chemical equation, which leads us to having the same number of atoms of each element on each side of the equation, or on each side of the arrow. So we change these big numbers, these coefficients, and the whole thing with balancing chemical equations is that we need to adjust these coefficients. And a lot of times it is a trial and error process. All right, which means it's going to take a little longer for you guys at first, but once you start to get good at these, they start to go quick, and then you start to notice some patterns. So this is one of those things where practice makes perfect. And, yes, I'm a geeky science teacher. I always kind of found this like a little fun. It's in a way kind of like chemical Sudoku. All right? Yes, there are more fun things to do, but, this is better than memorizing the organelles of a cell and what they do, or genome patterns or A, T, C's, and G's that you might do in biology. That's not as fun as this, I don't think. But that could just be because I like this a little more. So we have to be able to choose the right coefficients. All right. So if we look, again, the number of mercuries on each side is balanced, but the number of oxygens is not. So we have to get the number of oxygens balanced. And what we do is we would go in, and the easiest way to do that is to put a 2 in front of the HGO. And what this will do is this will make sure that I have 2 oxygens here, and that balances my 2 oxygens there. But adding a coefficient then changes other things. It now changes how many Hg's I have. All right? Now I have 2 Hg's on the left, so I got to go fix that. I can fix that by adding in a 2 right here on the right-hand side of the arrow and give myself 2 Hg's on the right. Now, if I take a look, all right, and sometimes it's nice that you could make a chart underneath this if you want to. You don't have to. But if I put those 2 2's in there, right, I have 2 mercuries on the left of the arrow, and there's 2 oxygens on the left of the arrow. So 2 Hg's and 2 O's. This 2 will distribute to each of those, like it would something in parentheses in math. And then on the other side of the arrow, I got 2 Hg's, which is exactly how many was on the other side. And I still have those 2 O's, which is what is on the other side. So now I have 2 Hg's on both sides. I have 2 O's on both sides. This is a balanced reaction. This is what I'm hoping for. And when you're starting out, sometimes it helps to pop the 1 in there, but we usually don't write the 1's. Just like if you have 1x in a math problem, you just write x. You don't write 1x. But if you have 2x's, you put 2x. Same thing with these coefficients. Although as you see and do the practice problems, I won't for my class at the beginning here be taking off if you're writing the 1's, because we're just trying to learn the process first. And it's easier to just erase the 1's at the end than it is to just try to not see them at all. So just don't forget that if you don't see a number, there's going to be a 1 there. Got a couple of guidelines for balancing equations. I'm calling these guidelines because they're not hard and fast rules. All right, there's essentially 4 of them. Remember, you have to have the same number of atoms on each side. That's the whole point. You cannot change, remove, or add subscripts. You can only change coefficients. And the coefficients go in front of chemical formulas. You never put them in the middle of a formula. They go before the whole formula. All right? And those are pretty hard, fast rules. That's why I numbered them 1, 2, 3, 4. The other part, these few extra tips, these are definitely guidelines to follow. They can help. The best way to learn how to balance equations is to balance equations. And so kind of balance out the big formulas first. Try to keep the biggest, scariest looking formula with a 1 in front first if you really don't know what to do. And then if you can't make it work with a 1 in front of the big, scary looking formula, then go to a 2, then go to see if that works. And if it doesn't, go to a 3 and go from there. Because usually the most complicated looking formula will have the lowest coefficient. Usually. Not always the case, but that will kind of help. If you see the same polyatomic ion on each side, a lot of times these polyatomic ions are in parentheses, so it tips them off. Treat it like it is a whole unit. Don't break it out. So if you see nitrate ions, which are NO3s, all right, if you see NO3 on both sides of the arrow, treat NO3 as its own NO3 thing. Treat it as one thing instead of treating it as 1 nitrogen and 3 oxygens. Because a lot of these polyatomic ions have oxygens, and it makes oxygen a total pain to do. And there's no one particular way to balance. So, trial and error. All right, let's do some examples here. All right, we are going to start here. We got magnesium plus oxygen gas giving us magnesium oxide. So starting out, there's 1 Mg on the left. There are 2 oxygens on the left. If I look on the right, we have 1 Mg and we have 1 O. I like to draw a dividing line down the center. All right, obviously, what I can see right away is I got 2 oxygens on the left, only 1 on the right. The only way to fix that is to put a 2 in front of there. What that does is that changes my magnesiums to having 2, my oxygens to having 2. Now my magnesiums are not balanced. So I have 2 on the right, only 1 on the left. I'm going to put a 2 right here. This gives me 2 magnesiums. If you look, now 2 magnesiums on one side, 2 on the other. They're good. 2 oxygens on one, 2 on the other. They're good. I can leave that line for the oxygen, the O2, blank, because leaving it blank means there's a 1 there. All right. If you really feel like you need to put the 1 there, go ahead. That's fine. Alrighty. Let's look at the second example. CaCl2, calcium chloride, breaking apart into calcium and chlorine. All right. Let's draw my little line there. I have got 1 Ca and 2 Cls. And then on the other side of the arrow, I have 1 Ca. I have 2 Cls. 1 and 1. That's good. 2 Cls and 2 Cls. That's good. This equation is already balanced without writing any coefficients, and that's a totally legitimate answer. And again, if you want to put the 1s in, put them in, but you don't need them there. All right, and early on. Eventually, I will get to the point where I might start taking off for those. All right, later down the road, or if you go on and take a more in-depth chemistry class where you're balancing equations again, you don't want to write the 1s. But for right now, as you're learning the process, I'm not going to worry if you're writing the 1s. All right, and this one was balanced already, so that's great. All right. Let's look at some more. Couple more examples, right? Let's do this. These arrows are nice and centered, so I can do the 1 line. I'm going to break them out one at a time. All right, these are a little more tricky. I have 1 Na, 1 Ca, and 2 Cls on the left-hand side. On the right-hand side, I have 1 Na, 1 Cl, and 1 Ca. So if I look right away, it looks like my sodiums are good, it looks like my calciums are good, but chlorine is not. So I have to somehow, I have 2 chlorines on the left, I got to get to 2 on the right. The only way I can do that is by dropping a deuce right in front of the NaCl. So I pop that 2 right there, that gives me 2 Cls and 2 Nas. Well, because it gave me 2 Nas, I got to drop another deuce in front of the Na and put the 2 right there. It gives me 2 Nas. Now, if I look, 2 Nas, 2 Nas, that's good. 1 Ca, 1 Ca, 1 calcium, that's good. 2 chlorines, 2 Cls, and 2 chlorines right there, 2 Cls. It's all good. There would be 1s right next to the CaCl2 and the Ca. And now that one's balanced. All right, here's a big one. All right, we got potassium phosphate and magnesium nitrate making potassium nitrate and magnesium phosphate. One of the things I want to point out with this one right at the beginning here, notice this PO4 stays together in the parentheses over here. And this NO3 stays together right here. So instead of counting all the oxygens, because there's oxygen in everything, what I'm going to do is I'm going to keep those polyatomic ions together. And the big tip-off that they're polyatomic ions is at some point on each side they are in parentheses, even though they're not in these two. All right, so let's write down just like we've been doing and see what we have. I got 3 Ks, 1 PO4. Remember, I'm keeping the PO4 together because it doesn't split up. 1 Mg, and I got 2 NO3s. Let's look at the right side. There's 1 K and 1 NO3. There's 3 magnesiums, and there's 2 PO4s. It doesn't look like anything is balanced. All right, we got a 3 and a 1. We got a 1 and a 3, a 1 and a 2, and a 2 and a 1. So nothing's balanced to start. This is one of those situations where I am going to look at what I think is the craziest looking compound, the most difficult compound, and that would be this right here. For me, there's 3 magnesiums, 2 of a polyatomic ion. All right, I'm going to try to keep this at a 1. So I'm just going to start right here, and right here you can see that I have 3 magnesiums. If I'm keeping this at a 1, let's start with the magnesium because it's first thing there. So I got 3 magnesiums here. That means I need to get 3 magnesiums on the other side. I'm going to do that. I'm going to change my colors up a little bit. I'm going to put a 3 right there. That changes my number of magnesiums to 3, and it changes my number of nitrates, my number of NO3s, to 3 groups of 2, or 3 times 2. And where I come from, 3 times 2 is 6. Now, I'm going to just stick with what change I made. I made this change where there's 6 NO3s. On the other side, there's only 1, so I need to put a 6 here. Get rid of that 1. That gives me 6 NO3s. It also gives me 6 Ks. So this made the change of giving me those 6 Ks. On the left side, I have 3 Ks. Well, what times 3 is 6? 2 times 3 is 6. It's almost like a song. That also changes my PO4s to 2 PO4s there, which is exactly what I already have. So there is a 1 in front of the Mg3PO42. I am done. 2, 3, 6, 1. All right. Taking a deep breath and going slowly really helps with these. All right. Here are some practice problems. All right. What I'd like you to do, pause the video, write the problems down, leave yourself a little bit of space, and then answer them. And then come back and start the video up again, and I'm going to do a quick explanation. I'm not going to write the stuff on each side. All right, I will kind of show you how I am going to go about doing everything. All right. So, for this first one, all right, this first one is kind of tough. All right, there's a lot of different things going on. Oxygen's in a few different places. All right, and what I can see right away is that, there's 2 oxygens there. I'm not going to try to balance the oxygens in the first place, but what I notice is that on the left side, the only place oxygen has a subscript of 2. That means it's going to be an even number because it's only whole numbers that go in front of things. So I'm going to need to make sure I have an even number over here, which means I got to get this 3 to an even number. So I'm going to put a 2 there to give myself 6 oxygens there in the Fe2O3. And what that's going to do for me is that is going to make me have 2 times 2, or 4 Fe's, 4 irons. On the other side, there's just 1 Fe, so I got to put a 4 there. That gives me my 4 irons, my 4 FEs. That 4 gives me 4 times 2, or 8 S's. I'm going to go over here, I'm going to put an 8 for the S's to give myself my 8 S's. And now here's where the complicated math comes in, and I'm going to use some of the space below. I've got 2 times 3, which is 6 oxygens. There's that plus sign, plus 8 times 2, which is 16 oxygens. 6 plus 16 is 22 oxygens. And this is just on the left hand or the right hand side. All right. What is 22 divided by 2? 11. And so an 11 goes there. And so I get 4, 11, 2, 8. All right, let's move on to this next one. We got H3ASO4 going to AS2O5 plus H2O. All right, again, a couple different things. I'm going to start right here with the AS's, because I have 1 AS on the left, 2 AS's on the right. And what that's going to do is that means I'm going to have to put a 2 here to get to those 2 AS's. Putting that 2, I'm going to save oxygen to the end, and hopefully it'll work out for me, because there's oxygen here, and there's oxygen here, and there's oxygen here. There's oxygen in everything. So let's balance the other things and see if we get lucky. So 2 times 3 is 6 hydrogens, which means I need something times 2 to be 6. So I need to put a 3 right there. What this gives me is I'm going to take this space below again. I'm going to write out my oxygens. 2 times 4, there's 8 oxygens on the left. There's 1 times 5, 5 oxygens, plus 3 oxygens is 8 oxygens on the right. And so those oxygens were kind of taken care of for me. So they looked like they were going to be a pain, but by balancing the hydrogens and the arsenics, the H's and the AS's, we got everything balanced. All right, move on. Number 3, C10H16 plus Cl2, giving us C plus HCl. This one's a little bit weird on its own as well. All right. And everything on the right-hand side has a subscript of 1, so I just have to balance it with these numbers here. All right, so let's take the scariest looking thing, C10H16. Let's keep a 1 here, which means there's 10 C's, so I have to put a 10 here. And there's 16 H's, so I got to put a 16 here. That gives me 16 Cl's. 8 times 2 is 16, and that all worked out real nice. All right, so, I hope you took my advice, paused it, tried them on your own. Hopefully you figured them out. You did them well. That'll be real nice. And then, there'll be some more practice on this. And if you have questions, reach out to myself if I'm your teacher, or whoever your teacher is. We'll be happy to answer them. Have a good one.